So I will just focus on a small aspect of structure formation and using basically what Tom has been introducing for simulations of structure formation in warm dark matter cosmologies. Just to have one introductory slide. What Tom was just introducing is the dark matter sheet. That is, if we have an initially perfectly cold collisionless fluid, or not collisionless, it is initially distributed only on a three-dimensional hypersurface in 6D phase space, and the idea is now that we connect this up rather than sample it with particles. And what this looks like in 2D is slightly easier to visualize. So we start now in 2D, it's a two-dimensional surface, and we start connecting up triangles. The perturbation spectrum ripples this a little bit, and then if you let gravity do its thing, this will do origami basically and fold onto itself. And the advantage of tracking the distribution function explicitly, Tom has shown many examples of this, gives you a volume filling information rather than just information at the vertices. And yeah, so you can track the folding basically of the sheet over time. And why do we think this is interesting now to combine with warm dark matter? So warm dark matter, for all practical purposes, warm and cold doesn't really fit. So I was talking about the perfectly cold limit, but warm dark matter basically only means here that instead of the CDM power spectrum, we have a spectrum that has a small scale cutoff. And so if you look at the dynamical range of a simulation, you're on one side limited to the box, and on the other side you're limited by your resolution element. With a warm dark matter model, you can capture the whole range of perturbations with your initial conditions. And then you treat it in the cold limit, because we don't really understand yet how we can go to the warm limit. Probably doesn't matter. So basically, the warm dark matter just truncates the spectrum, and then we treat it as a cold fluid, like everyone does. Tom has shown this slide. What people have tried before was adaptive softening, which gives you still noise in the particles, and if you do this tetrahedron deposit, all this noise is gone. So how do we turn this now into a new simulation code? So basically what we have now is we have particles that span these resolution elements, which are the tetrahedra, and we have the mass of the tetrahedron, which should be spread out uniformly. Now it's very hard to compute the force of a tetrahedron onto a particle. So we do a little trick. We can approximate the mass distribution of these tetrahedra either with a single particle by putting it at the center of mass of the tetrahedron, or up to quadrupole order with 4 particles. Quadrupole order then also represents linear deformations of these tetrahedra accurately. And then once we have this, now we have 2 kinds of particles. We have tracer particles, the ones that span the resolution elements, and we have mass-carrying particles, the ones that deposit the mass, and they're not at the same places. What's the advantage of doing this? Or why do we care? So the problem of these warm dark matter simulations is that usually when you run them with the standard method, they don't look like the pictures I've shown you before, but they look, and it's well known, they look like this thing that you see here. So it's fragments, you form small scale structures that shouldn't be there because there's no perturbations on these scales. You're in the perfectly cold limit, meaning all this regime is basically unstable to any kind of perturbation, although there is no perturbation. So if you have a method that introduces noise in any kind of coherent way, that will just lead to fragmentation. So you can picture this. Why does this happen in filaments? It's kind of easy to understand. It's just if you think you have some kind of particle lattice and then you anisotropically compress it, then you'll get some modes that you excite. And if you do not soften along the non-collapsed dimension, then these will just form clumps. At the same time, you don't want to have such a bad force resolution that isotropically spans along the non-collapsed dimension, because you want to resolve the structure in the other directions, right? If we connect up now these elements, what happens is that the mass gets not deposited at those clumps, but gets spread out uniformly. ideally uniformly. There's slight noise still if we use the particles, right? So the advantage of what this is now, if we do a plane wave collapse solution with this, we see, so this is just a plane wave at shell crossing, just using, I believe, 32 cube particles with 256 cube force mesh, and then a very high, so you see the particles start seeing each other, they start scattering. With the two other methods, now the mass is not deposited where the tracer particles are, and the thing is perfectly on the analytic solution. And so if you look at the top panel here, you can do a convergence plot. You keep the mass resolution the same, and you just crank up the force resolution. And what you should see is, of course, that you get closer to the analytic solution within some limit, because you're not actually introducing the number of tracer particles. So it's not going to go completely down to 0. What you see is for the standard PM methods, you actually your error doesn't even reduce at all as you do this, but it increases. While now with the new method, this looks much better. At the late stages, once we have one-dimensional, so in one dimension we cannot get chaotic mixing, so we just get the winding up of the sheet. The top panel is a particle mesh method. If you crank up the force resolution, particles start seeing each other, and you get scattering in phase space. And you basically destroy the coherence of this spiral. If we maintain explicitly the knowledge of the distribution function by connecting up things, this problem is basically gone. And it also cures this fragmentation problem in warm dark matter. So what you see here is, again, from left to right, we keep the mass resolution the same. We crank up the force resolution. Top panel is standard PM. This is just the magnitude of the gravitational force that you see in these panels. And so you have, in all these filaments, all of a sudden, these fragments show up. As the particles, obviously, you over-resolve them in some sense. And then they start seeing each other in these regions of anisotropic collapse. You fragment. And with the new method, explicitly tracking the distribution function, this disappears completely. So Tom already pointed out that there is a problem to this. So this works very well in the non-statistical, non-kinetic regime, basically, the non-statistical mechanical regime. Where we have in the ordered flow regime, we don't have strong mixing, so everything's fine. As soon as we have kind of mixing, you see what's happening. So this is just a blob that's advected, so this is just fakes mixing. If you put in any kind of line element, the line element will get tracked, but it has nothing to do with the growth of the surface of the distribution function. And so this leads to these problems that Tom has shown. But it completely cures fragmentation. And so we can now try to measure for the first time, probably in the absence of artificial fragmentation, the mass function of halos. But the problem is, if you don't fragment, now you can have very dense filaments. So if you start friends of friends group finding, all of a sudden you find halos, and they're all connected by dense filaments, because everything collapses first to a filament before it goes into the halo. And so that's a problem you have to overcome. Once you have overcome that, you get the halos. But we're still not there. So this just, the top panel illustrates the solution you get with a standard 3 PM. So you get fragments everywhere. If you do a PM with very low force resolution, those fragments are also gone to a large degree, and this is the new method which doesn't show any of this. So this is now, on the top panel here, you see the mass functions. The black line is the CDM, and then the red shows all these fragments, and the other two methods show a downturn. But why is there only a slight downturn and not a sharper one? So what we did is we inspected actually all of these objects, and what you see then is there is a clear distinction in terms of the properties of these dense structures. Going now from low masses to higher masses, you see that many of the low mass objects are just objects which are turning around in the second or in the third dimension. So just kind of starting to collapse, starting to isotropize, and so on. And as you go up in mass, they start being normal halos. And once you throw out all the objects that are clearly non-halos, which are in early stages of formation, or which are just kind of at the kink of a filament, you get a very sharp turn in downturn in the mass function, which is shown here by the green dots in the top panel. And so for this warm dark matter simulation now, what we get is a very sharp mass cutoff, and then you get at lower masses, you have a regime where halos are just forming, very rapidly accreting a lot of mass, and then very rapidly virializing, but only once they cross this half-mode mass scale. Okay, so we can do this now with simulations to get a mass function. Can we also do it analytically? This has been known for a very long time. If you do standard excursion sets with correlated walks, so just real space top hat filtering, you can't get anything that has anything to do with the warm dark matter mass function. So this is the dashed thin line that you see is what you get out of standard excursion sets with correlated walks, real space. You can do it. People know that you can do it with sharp K filtering, but that's, at least to me, it's not clear what that physically means. The interesting thing is that once you include the peak constraint that people have been discussing for a couple of years now, you get the downturn. So what you see here now, the black lines, the red is what we measured from the simulation. So you get a downturn, but you get a very robust prediction for a power law low mass tail of m to the 2/3, which you can't get away with a single barrier. So as long as your barrier only depends on the mass through sigma and so on, you cannot get rid of this. And so we're wondering maybe there is something more physical that's going wrong. So we looked at the densities of those proto-halos before they form. So this is, maybe you've seen in Robertson et al. Similar plots. So this is the overdensity of the proto-halo patch. And it should be 1.686 if all of these are spherical blobs. But of course they're not. So we get a scatter. So this is the density of the actual Lagrangian patch. Once we go to the spherical patch, so we measure the density of the spherical filter centered on the halo, the scatter increases, and we get a very large correlation with the velocity ellipticity, so the lambda 3 minus lambda 1. So the more anisotropic basically the strain field is, the higher the density. And this correlation is so strong that we can actually use this to get a very simple barrier, which is just density minus basically the largest versus the smallest velocity strain. And we get a new barrier. And there is no sign that there is anything special about the barrier apart from that. We can also look at the proto-halo shapes. They're all consistent with peaks. There's nothing special. Nothing seems to be different about these halos. If we do actually walks on, if we start the walks at the actual locations where we identify the halos, we notice one interesting thing though. So we're trying to predict the halo mass from the actual location, and we see there is a strong bias as we cross below this half-mode mass, kind of the scale where the cutoff in the power spectrum happens. And so this is a clear indication probably of what we've seen before. So the structure formation in these warm dark matter cosmologies is very different. So basically the object starts to kind of collapse and then viralize and accretes a lot of mass in a very short time. And so you have a very big uncertainty. If you have like any uncertainty on the collapse time, you'll make a very big mistake on predicting the mass. And so we tried to fold in such an uncertainty on the collapse time into the barrier. So you basically need a second barrier. You have one barrier that predicts you that an object will be collapsed, and you need a second one that ultimately predicts the mass given a certain uncertainty. If you do this, you can reproduce a sharp non-power law cutoff. But of course, it's not very physically motivated yet, and it would be good to understand this. I think it is interesting because this now gives us some leverage to the small scale behavior also in CDM. There's nothing different here in these simulations apart from the initial transfer function. It's a cold collisionless fluid like CDM, just a perturbation spectrum. And the other alternative, of course, that could produce something like this is assembly bias-like effects, so that all these low mass halos have some kind of environmental influence, and that's why we can't really predict their mass. Okay, I want to just finish with a short movie of the formation of such a warm dark matter halo. just so you get an impression of how this virialization and collapse happens. And so you see very quickly, then it virializes. And then there's a few fragments which come because this is a zoom, and so there was a bad sampling of the large-scale particle field. But what you see is basically there is no substructure in those halos that form at the cutoff scale. And you see all this winding of the caustics and so on that then builds the halo structure. Okay, so let me conclude. So I think it's very interesting to consider these new methods that explicitly model the distribution function, because it is the only alternative I'm aware of to particle sampling. It is currently limitedly usable, but I think it gave us already very profound insights, in some sense, I would say, into structure formation. Once we get rid of all these numerical effects in the non-heavy mixing, but in still the ordered flow regime. And then, so we could measure the mass function. Halo finding is now tricky because you have actual large-scale structure that is not in halos, that can be very dense, but is not in halos. And the interesting thing is that these simulations are also good to now check the excursion set models, because not only have we exponential leverage now at the high mass end, but also at the low mass end. So this helps to single out problems with these models. Thank you.
So people have been talking about this instability of self-gravitating sheets and the filaments.
Mm-hmm.
So why we don't see this at all here in the simulation? We understand that, analytically, if you do a little bit of perturbation theory on, a sheet or filament, and that is unstable.
So it is unstable, but there is no perturbation.
Well, at least there's large-scale perturbation. You still have, at least, the large-scale. I don't know. So that's you really need perturbation on the scale you're talking about, or in fact, you could have some, banding or whatever.
So this was something we were wondering about. So this could be explaining why not all of the halos get the right mass, or we don't match actually all of the objects. Maybe there is higher order catastrophes that lead to halo formation in these. So you have kind of a bending, and then so it's not a peak, but it's kind of a bending. But then all of the proto-halos seem to be perfectly consistent with being peaks and not being some weird kind of topological feature.
One more question?
Yes, so these are, because that was a zoom simulation, and we had a coarsely sampled outside region. And that, once they get close, they excite.